time. Last time we reached the grid. So we used dissipation minimum theorem to calculate not find bounds for resistance between 2 points on a grid of infinite grid of resistors. And I said probably that we'll be calculating exactly as well, right? But I think before we do that, let us do something else before, because logically speaking, what we were doing were integral methods. And we did some of them. These are the dissipation, this is basically mostly the dissipation minimum theorem. But there was planned still for a few more, like reciprocity theorem. I don't think we talked about reciprocity theorem, did we? No. Okay. So let us take, before we go to infinite grid, let us do reciprocity theorem. And still after that, then probably also not the first thing we'll be doing after that will be the infinite grid. We still have a little bit before that. But okay, let us start with reciprocity. So what is reciprocity theorem? It's basically a very simple thing. In intuitive terms, that you know, in optics, not optics, electrodynamics, we have equation for electromagnetic waves. These are Maxwell equations, and then in practice, you know that if I can see Tudor, then Tudor can see me, right? So how comes this out from the equations of electrodynamics? That's exactly what is called reciprocity theorem. It is reciprocal. So, but let us take a little easier version of that. This deals with a resistor. And then let us have four terminals here. Arbitrary. It can be a set of resistors. It can be a continuous medium with 4 electrodes. And then we have electrode 1, 2, 3, 4. 1, 2, 3, 4. And then we apply, let us say, we let in current I here and take out from there. And then we measure voltage here between 3 and 4. And this will be B3, 4. And then this will be proportional due to linearity of the rule. This will be proportional to the current here. And this will be certain, effectively, it will have dimensions of ohms, the coefficient of proportionality. It will be something like R3, 4, 1, 2. We let current in between 1 and 2, measure between 3 and 4. And then current which goes there, I1, 2. And then on the other hand, we can now measure, let current in here, take out here, and measure voltage here. And then we will be having V1, 2 equals certain other coefficient of proportionality, R1, 2, 3, 4, times I3, 4. Now, what reciprocity tells us is that those two are equal, those two coefficients. Now, the question is how to prove it. This is a global property of the piece, right? This doesn't come out from considering a single vicinity of any of those electrodes, because the coefficient of proportionality obviously depends on the total shape of the conductor. where the electrodes are placed. So it's a global property of this configuration here. Now let us try to derive it. And so let us write equations at hand. So we have, let us consider first distribution. Let this be, this will be described by potential psi, and here this one will be, distribution will be phi. First configuration of potential will be phi, and second one psi. And then we have now J. Yeah, let's see. First, current density be I, and second be J. Then we have I is a gradient of sigma gradient of phi, and we have now divergence of I. Divergence of I will be the points where we inject and take out current, and so it will be now the current that we inject I, and then there will be Dirac delta function, because we have singularity where I inject and when we take out, and then divergence of I will be Dirac delta function of R minus R2. Well, no, R1 we have, well, we have divergence. Here we have convergence, here we have divergence. So R1 will be plus R1 and minus Dirac delta R minus R2. Is that right? Do you agree? Is it okay?
I mean, I'm not sure about the sign either, but it, yeah.
As to what else, if we have current divergent, then we have plus, because it's divergent. It's not convergence, but it's divergence. So here, if we check here, the current here is divergent. Right? So this is a plus divergence, positive divergence. And then let us write another equation. We still let us plug in the expression for I. So this will be now divergence of that. Divergence of sigma gradient of phi. And then by similarity, we can now immediately write another equation for the second case, which is I. And now we have Dirac delta function of R minus R3 and minus Dirac delta function R minus R4. And now this is the gradient of sigma and divergence of sigma gradient of psi. Right? Two equations. Now what we do is we multiply this here by psi. And integrate over the whole volume. So we'll be having on the one hand, we'll be having integral of gradient, divergence of psi gradient phi, and multiplied psi dqr, and let us see what it is. Or maybe first we do, let us apply the same thing to the right hand side. Right hand side will be integral of that, but out of that the Dirac delta functions goes away. I obtain here I multiplied by, but because I multiplied by psi, it will be psi at the side of R1. Okay, let me write it wrong, long first. So I is constant. psi, Dirac delta function of r minus r1 minus Dirac delta function of r minus r2 dq bar. But this is psi of r. And so is left here from this term gives non-zero if r equals r1, and then this becomes psi at r1. And with this we obtain minus psi at r2. Right? And this is voltage. This guy here is voltage V12. Isn't it? This is a second case with psi and voltage between 1 and 2, V12. And now we integrate left-hand side by parts. And if we do that, then we'll be having certain surface integral of gradient of sigma psi gradient of phi. No, this is not this. Oh, not this. And surface integral dot d surface element. Yes. Because this is now we take divergence of the whole thing. Divergence of the whole thing, but if I integrate over volume, this gives me surface integral, right? And then goes the other part with minus integral sigma gradient of psi phi.
We're keeping conductivity constant.
No, I'm not keeping, so that's why I started fixing it. So conductivity is not constant, but here this is applied to sigma, right? So this was applied. This was applied like that here, right? I multiplied it by star. And then now I apply the whole thing that is here, and I subtract when nabla is applied to that phi.
Okay, yeah.
So now it will be applied to psi, and this will be sigma gradient of phi gradient of psi dq bar. Now what next?
I think you can apply it again.
Yes, exactly. That's what I'm doing. We apply it again. Now, first about this. So what we do have here? Here is sigma gradient of phi is current, but current cannot have a component across parallel to perpendicular to surface element. So this cross product is actually zero, right? That's a boundary. So this goes away. And now we do the same thing before, integrate by parts. So what we want to do, let us see what we want to do.
I think take the nabla from phi and move it over to sigma psi.
Sorry?
I think take the nabla from phi and move it to sigma, sigma nabla psi.
So we had this, and now we want to have phi out. So I want to take phi out, so we take nabla, this nabla here. take phi and apply to everything else. So now this will be minus integral, and now this nabla is applied to everything. So we did sigma gradient of psi dq ds and a plus. So now it's the second time we take this minus is plus now, and now that nabla is applied to everything else, which is then integral of phi and gradient of sigma gradient, divergence sigma gradient of psi at equal bar. Okay, and now we had another equation that I wrote, and this is well, I didn't write yet, but that's the one I did write. So this is this guy over here, and now we have exactly the same guy over there. Right, these are the same things. So now I can take this expression from over here. I take this expression from over here. And this goes into here. And so the whole thing now becomes I is constant integral Dirac delta a minus R3 minus Dirac delta a minus R4 and then we have still phi left, and phi is a function of coordinates and dq bar. And now this becomes a voltage in the first case at position 3. So this is now I multiplied by phi at R3 minus phi at R4. And this is I, and V 3, 4. And so now bringing things together, what we have is we have this here equal to that one here. So I is the same, V12 is V34 if are the same. If this equal to that, so this equal to that, these are equal. So we conclude that now if I12 equals I34, then V34 equals to V12 because that R34 12 equals R12 34. And we prove it. So everything okay?
Is this true for impedances as well?
Sorry?
Is this true for impedances as well?
Sure. Of course. Because, well, there are impedances you can just everything what you have for resistors you have also for impedances. So how is it? Is everything normal? Photo? Raise your hand if it's clear. Okay, good. Now we have different other similar theorems as well. Perhaps you know some similar theorems. Reminding this reciprocity theorem. No one knows. Johan, maybe you know.
No.
Something similar to this reciprocity what I have here in some other case in physics. Jan, do you know anything?
No, sorry.
No, okay, well, that's okay too. What about mutual inductance? Remember still what it is? Raise your hand if you remember what is mutual inductance. Okay. Otto, what is mutual inductance? Maike? Come on. Johan, you are our last, well, we have here Tudor who raised his hand, but other than that, you are our last hope.
I don't know circuits, sorry.
Mutual inductance. Okay, mutual inductance we definitely did have during our electrodynamics course. I don't remember exactly where, but you surely remember what is inductance. So, Otto, what is inductance? Maike, what is inductance? Johan, what is inductance?
It's the thing you use to calculate the magnetic energy in a coil.
Okay, good. That's already a good point. But more specifically, this is coefficient of proportionality between magnetic flux through a loop and the current in that loop. So if you have a coil and then magnetic flux, total flux through that coil, but you need to keep in mind that because coil has many loops and each flux goes n times through the loop, so you need to multiply the number of times it goes through. So you have certain flux going through it, and if you coefficient of proportionality between flux and current, that's it. Now there is mutual inductance, which means that if you have more than one loop, then current in one loop will induce a certain flux through the other loop. And this is called mutual inductance. And yeah, since you don't remember, let us recall what it is. So you have one loop, current I1 goes here. Then you have another loop like that, and then current I2 goes through that. And then the first loop will create certain magnetic flux that goes in through itself, but also through neighboring loops. And blue loop does the same. So you have current from there. Okay, now I cannot guarantee screw rules, but never mind. Just to draw the arrows randomly. And so we have flux from one going through the other. And so we have phi flux through first loop through the first loop is equal to, and because of the linearity of our equations, the Maxwell equations are linear. Then phi one flux through first loop is made of two components. Current is the first loop and coefficient of proportionality first, L11, meaning that loop one causing flux in one. Current in one causing flux in one, and plus another contribution, I2, L12. And then psi 2 equals I2 L22 plus I1 L21. Now, do you start recalling something? No, not yet. Maike, no, nothing. Other guys? Other universities? No?
Somehow.
Okay, so it was not my fault of teaching that you don't remember, because it seems it's everyone the same. Johan, did you remember something?
I am not sure I've studied this. Or at
Okay.
least I can't remember.
Okay, but normally it is in electromagnetic curriculum it is. Well, so what we have is equality L1, 2 equals L2, 1. And normally, during my electromagnetic course, I am also proving this equality, but proving a kind of, how to say it, from energy conservation law. So we see that this must be satisfied, otherwise we wouldn't have energy conservation law. But it leaves a little bit unsatisfied that how comes this comes out from Maxwell equations. So if this were not to be satisfied, energy conservation law wouldn't be valid. On the one hand. On the other hand, how it is connected, because all those fluxes can be calculated based on Maxwell equations. So how this is connected to Maxwell equations, or how it derives this from Maxwell equation. So answer how to derive it from Maxwell equation is again in the same technique before. So you write equations from one case, you write one other case, you multiply, integrate over the volume, and do it. And actually, this is already written into the lecture notes. So this part is in there. But I doubt it's worth doing here. You got probably the idea how to do it based on the reciprocity theorem what I showed you before, right? You got the, hopefully the hang of it, how to do it. So you can read it in the lecture notes, how you do it in the case of mutual inductance, but let us keep it here. And meanwhile, I'm still showing you how to do this from energy conservation law. From energy conservation law, you first you consider energy, total energy of the system. And then we have here let us calculate how we make electrical work to reach this state what is drawn here. So first we have no current, nowhere. And then we start increasing the current in the first loop. So we have electromotive force is minus d phi over dt. Flux through the first loop, E1. And now we keep I2 equal to 0 and increase first current. And then from this equation here, we have this will be L11 is constant, so it will be minus L di1 over dt. Now electrical work done, dW, is this is voltage once we make a full round along the loop. So work done is a charge multiplied by voltage, right? So this will be E1. Okay, let us only the plus side. So let us put minus here to have plus in total. So multiplied by dQ1, charge which goes through the first loop. Voltage multiplied by the by a small current, a small charge which goes through. And now dQ1, let us multiply. Let us plug in E1 here now. So this will be L di1 over dt dq1. But now let us combine this dt with dq. And then we have L I1, because I1 is dq1 over dt, di1. And now we integrate, we obtain work done. If we start from 0 and end up at a certain final current I1, is integral L I1 dI1. This is Li1 squared divided by 2. Probably that formula you remember, right? At least I think Johan remembers because you mentioned something about those lines. Johan, that formula you're familiar with, definitely, surely.
Yes, that I remember.
Now raise your hand if you think you remember that formula. Okay, Otto, you don't remember? No, it was too long time ago.
I remember I have seen it, but
okay, it seems like we need to train more during our ongoing courses. Mike, what about you? You remember a little bit? Okay. And so we calculated current, the white was that we did with a single loop. And then we say that, okay, what we obtained here, where did our work go? We made, performed certain work, where did it go? And we say that it went to the energy of electromagnetic field, or magnetic field more specifically. And that we, I think we already showed you equivalence of energies, like we had charge. Okay, never mind. We can, in the case of electrical field, we had two ways to calculate energy of configuration of charges. One was that it is we have electrical field energy density, which is E W. Energy density of a field, W is 1/2 epsilon naught E square plus B square divided by mu naught. So one way was to say that it is energy of a field comes from the field itself. The other was to say that we can calculate it like charge multiplied the potential. So we have two equivalent ways of calculating it. And with the magnetic field, we have kind of similar thing, but I think we didn't discuss it with magnetic field. Either way, that we can say that the energy what we created goes into the energy of the magnetic field, that V squared divided by mu naught. That's why all the electromagnetic electrical work also did went to the magnetic field energy. Now, next step. Now the next step. Now we have I1 is constant, we keep it constant, but I2 we grow from 0 to I2. Similarly to how we first increased I1 from 0 to I1. And then we have another expression for the W. We start with the same way that it is now minus E1 dQ1. But now, if we plug in d phi over dt, so this is d phi 1 over dt multiplied by d1. Now we have I1 constant. Now this is constant, but this I2 is changing. So from time derivative, that I1 drops out. So this will be now L12 di2 over dt dq1. And we do the same thing that we combine dt with dq. And then we have L12 I1 di2. But our process is where I1 is constant. So now if we integrate now, delta W, that we do now, equals integral L12 I1 di2 because I1 is constant, it becomes just L12, I1, I2. All right. So that's the total energy now. W total is the sum of those two that we had, and namely L1, 2, I1, I2 plus L11, I1 squared divided by 2. But we did forget one thing. What did we forget? Tell me. Yes?
Energy in the second loop.
Yes. Because while we increased the current in the second loop, we had to do also electrical work in the second loop. To complete, let me draw also for things to be more clear. Let me draw here equivalent circuits. So we had first loop, and we have here current sources. These are the current sources that make the work. If current is constant, no work is being done because voltage is 0. As soon as we start increasing, then we need to make work. So something like that. Those two is L1, is L2. Now for brevity, actually, we use here L11, but actually L11 we usually drop second index, and L2 is L22. And yes, we did forget the contribution from the second loop, but do we need to calculate? Maybe we already know the answer. What is that? Yeah, Tudor knows. Otto, what should I add here to make it correct? So we are missing here work we did in the second loop during the second stage. So first stage, we get I2 0, increase I1 from 0 to I1. And we calculated the work done as it's L11 I1 squared divided by 2. At the second stage, we get I1 constant, decrease I2 from 0 to I2. And then we calculated which work we need to make in the first loop to keep I1 constant. Because we have mutual inductance, while we increase in the second loop the current, there will be flux change through the first loop, which means that there will be a certain voltage in the second loop, which means that to maintain the current constant, we need to apply a certain voltage. But because current is flowing, maintaining voltage requires work. And that's what we calculate. But we did not calculate how much we need to make work in the second loop, because in the second loop also flux is changing now. So how much did we increase, Norman?
Can't you just do the exact same thing?
Yeah, sure. And the answer is?
It's plus L22 I2 squared over.
Exactly. So let me add it here. L22 I2 squared divided by 2. Very good. Now, but remember what we wanted to do. We wanted to show that L12 equals L21. So how shall we do it now? Tudor knows.
What's the question?
Sorry?
What's the question?
The question is, let us not forget the big picture. The big picture, why you started doing all this boring stuff. And that's because we wanted to show that L12 equals L21, right? Remember. Now, how do we complete this now? How it completes the proof? Johan.
Oh, no.
No idea?
No.
Anyone here in the class? Raise your hand if you got highest grade in physics, in electromagnetics, electrodynamics. So everyone, what did you get? Physics grade for what? You didn't have it.
No, I don't remember. I don't remember what.
All right, Tudor,
in electronics.
tell us what do we need to know now.
Well, we do the same thing, but we start with the second loop.
Exactly. So we repeat the procedure, but in reverse order. And the good news is that actually we don't need to do it because we have answer already. We just swap the indices, right? We just swap the indices, and we conclude that if we do it in reverse order, then we obtain, of course, L21, because this is only asymmetric part, I1, I2, plus L11, I1 squared divided by 2 plus L2, I2 squared divided by 2. And now, because apparently the total energy shouldn't depend on the order of how we do it, then this guy here must be equal to that guy here, meaning that L12 must be equal to L21. Must. So if it's not, then we don't have energy conservation law. Now, total is satisfying proof. No, it's for you. It's definitely not.
It kind of is.
Johan, is it a satisfying proof?
It's satisfying enough to me.
Okay. You are good for physics to go. If you were to say yes, then I would approve you for also for maths. But if you are completely already satisfied, then you are not approved to maths. But you are approved for physics.
Good. That's all I need.
Okay. Now the other and more satisfying possibly proof is in selection notes, how you do it from Maxwell equation. Now, another question. I had interesting discussion with our maths lecturers. But before we go to that, let me now write it. Think before down. Because L12 equals L21, if we have only two inductors, you usually denote it through M and call this is a mutual inductance. If you have more than one, then you probably need to just keep as many indices as you have over there. But if it's only two, then we can call it mutual inductance. And now, let us have a look on expression for energy. So our energy, let us call it now, which U maybe, potential energy, or field energy. U is L1I1 square, 1/2 before the brackets, plus L2I2 square plus M, 2M L1 L2 I1 I2.
Oh, M is just half. Oh, I see.
1/2 is over there. And now, what we would like to ask is if it's possible to have any. So how big can be mutual inductance? Basically, is the question. Because look, our current actually can be negative. We just reverse direction, it becomes negative. And we have a term that can be both positive and negative. That MI1, I2, this can be negative as well, right? So if we make M very big, then
you can be negative.
Can be negative, but that cannot be because if you remember what energy was, it was a field energy. And actually this guy here is integral of E square epsilon naught over the volume and 1/2. That's what it is. And this is definitely cannot be negative. Right?
We just need negative epsilon.
Okay. let it give still possible. Okay, in principle, yes, for high frequency fields, you can have negative epsilon as well, but let us keep it for the time being as is.
So M has to be lower than both L1 and L2.
And now the question is, yes, now the question is exactly, can you, from this, can you find upper limit for, can you find an upper limit for M? How big M can be? And here exactly we are now on the topic what I discussed with our mathematicians. So the thing what we have on the whiteboard here, how would it be called in algebra? Linear algebra. Tudor. So what do we have here?
I would just call this an inequality. I don't.
No, it's expression, not inequality, but expression for energy.
A linear combination.
This is called quadratic form.
Is it?
Yes, it is. So, and the question is, what is quadratic form? Do you remember what is quadratic form?
No.
Okay, so things are not too bad because I thought it was only the fault of our Taltech maths, but it seems at Oxford they didn't teach it as well. Also, I think Taavet, I remember Taavet as if remembering what the quadratic forms are. Who knows?
I probably just don't know it by its name.
Okay, quadratic form. What is quadratic form? So you have a matrix A, and then you have a vector x. And this is something like x1, x2, x3, all right? And then you take product, x transpose A, x, a matrix product. This is called quadratic form because this is sum Aij, xi, xj. This is like a homogeneous quadratic polynomial. This is called quadratic form, and they are positive definite, negative definite, non-positively determined, positively determined, negatively determined, non-positively, non-negatively, and undetermined, meaning about which signs they can take. Now the question is, how can you figure out for a given matrix A, which kind of situation we have? Is it positively determined? Is it negatively determined or undetermined? So, and what this means positively determined? It means that whichever x vector you take, the result is always, and it can never be 0 or negative as long as you have non-zero vector. This is positively determined. And analogously negatively determined. And then you have you can have situation when it can take 0 even if x is non-zero. This is either non-negative or non-positive, something like that. Tudor, anything remember right now? We did have it in linear algebra. I myself I transferred to Moscow on second year, but the first year I had in Tartu University, and we did have over there in linear algebra course. And now the answer is, I'm not sure I know all the algebra terms correctly in English, but basically the trick is that you take main minors. minor is like a submatrix, right?
Okay, yeah.
Yeah, and the main, it's called main or something else, which is the upper left corner. If you take the minor as the upper left corner, I think it's main minor. Okay, so you have here, oh, sorry. You have a matrix A11, A12, blah, A1n, A21, A22, A21, and so on. So you take now a determinant of the whole matrix. Then you take determinant of a submatrix, which is n minus 1 times n minus 1 is upper corner, and so on. Then you have this, and the last one is just this. You have a sequence of determinants. And now, if all the determinants have the same sign, it is sign determined, either positively determined or negatively. So you have m, how we determine those minors? Don't remember?
Not really either. I think we would call them
M something like M,
M and J.
M, and then
IJ and where I and J are the column and row that are missing.
let me put here main minors. Something like M is means how many rows and columns they have. So we must have determinant of M1, which is just the element itself. Must be positive. Determinant of M2, which is this matrix here, 2 times 2, positive, so on, and the determinant of the full thing, which is the same as the determinant of A, must be also positive, and then it is positively determined. So, it's somewhat useful knowledge from linear algebra, since it seems almost none of you remember that, so I think that was useful in itself. Johan just left. He was still there, but... Oh, it's not coming. I want to get back. So, Johan, do you remember those minors from your lectures?
Very vaguely. Principal minors, I think it was called.
How they were called?
Principal minor.
Principal. I felt that the main is a wrong word. That's I felt it. Principal, yes, principal. Sorry. Principal minors. And so, yeah, sometimes things from mathematics become handy as well. And so applied this here. Actually, we could have avoided that. We could have just played with in our case, we could just take this, consider it as a polynomial of I1 and I2. And then require that it cannot be go to 0 for any I and I2, and then we have something like we can even take like divide everything by I2. Let us say then we have I1 divided by I2. Over there we have a quadratic polynomial now for that ratio. And then for it not to go to negative, the corresponding quadratic equation mustn't have real solutions. And then you have the conditions that discriminant must be negative, and you would obtain the same condition. But I thought this was just remembering this piece from linear algebra that is actually useful in physics here and there. Because it's of more generic. If you have, it is okay if you have only 2 of them, but if you have more than 2, then it becomes a little messy without. And so we have now our requirement L1 soil is positive, right? No problem with that. We just need to check the determinant. We have made determinant L1 M L1.
L2.
L2, yes, sorry. This determinant of that equals L1 L2 minus M squared. And that must be larger, or okay, let us let it also to be zero, but this means that the electric field must be everywhere zero. If this is zero, electric field must be everywhere zero, right? It's not very realistic if we have, we'll talk about this a little later. So we have conditions that M must be smaller than geometric average of L1 and L2. Yes?
Have people had an exercises on figuring out how to make M as large as possible, like how to put the coils next to each other to maximize energy?
Yes. Let us talk about that. Do you think you know any coils where M is as large as possible?
Yeah.
Yes?
Yeah, coil on top of coil.
Coil on top of
Or
coil.
maybe coil inside coil.
See, you know how, and how are those things called?
Solenoids?
No. They are called transformers.
Ah, right.
So basically, what this means, so we have M equal almost to square root and geometric average of those two. If E is everywhere zero, even so we have non-zero current in one of them. So if we have a certain loop and certain magnetic field around another and another field, so it means that they must cancel exactly at each point of space. So it means that field lines must coincide. The field lines of one coil must be exactly the same as those of the other coils, which means that this drawing is not good. We can have one option is like that. We have one coil, and here we have another coil that repeats exactly. Maybe the density of loops are a little different, but it's just the shape is repeated. In that case, both have the same shape of field lines, and if we take corresponding direction of current in one and other, we can the total current in the solenoid will be zero, and no magnetic field is there. Even so, we have non-zero currents. And this is one case. The other case is we make this using the magnetic core. You may remember, you may not remember, but ferromagnetic core attracts field lines. So if you put here a certain loop around, current around it, the magnetic field lines will stay inside. So it just doesn't matter too much what is the shape of this currents over there, but field lines repeat the shape of the magnetic closed magnetic core, meaning that now if we put here another loop over there, the field lines have the same shape. And again, you can reach a situation when there is almost no magnetic field if you have opposing fluxes created by one and the other. So both here and there, M is just L1, L2, geometric average. Okay. Now, one more fun fact is that, sometimes you use the first solenoid, like without ferromagnetic core as well, as transformer. When you might want to use the transformer without core, what do you think?
Space issues?
Because you have dissipation or due to Foucault currents, you have possibly more important, you have non-linearity. If you want to have a completely totally linear response, meaning that you let sinusoidal current into one loop, and you want to have a linear sinusoidal voltage appear on this other. if you take that ferromagnetic core, it is not strictly sinusoidal because the core is non-linear. Mu, the permeability depends on magnetic field strength. So it is not completely linear, meaning that if you let sinusoidal current in, voltage that appears on the second loop might not be exactly sinusoidal. And sometimes you might want to avoid it. You might want to have exactly sinusoidal, in which case you take this so-called air core loop, air core transformer. All right. Now, yeah, and those the configurations air core is also used in one practical device. That what you might have or might not have at your home. Now, how it is called in English? I'm not sure about it, but something like leakage current. Probably not. I need to maybe need to Google fuse. So meaning that I think it's called still leakage current, probably. Maybe not. Maybe not. So the idea is that if you have your home electricity, and then you have there when you have connected to the outer network, you have all the fuses that your current cannot be larger than something. If you short circuit something, the fuses disconnect you, and you will avoid burning things where your short circuiting takes place. But there is also a device which switch your electricity off if you have so-called leakage current. Suppose you have somewhere some electric device has the phase wire connected to the body of the device, and you touch it, and then you will get electricity subject to the voltage. What is that? 230 volt, and that is very dangerous if you, particularly if you have bare skin and grounded well. Then you have when it becomes dangerous is that when current that goes through is larger than 30 milliamperes. So that device switches off your home electricity at the moment when the difference of currents in incoming wire and outgoing wire is larger than 30 milliamperes. So suppose here is your electricity comes in, and here it goes out, and here is your home device. So here is 230 volt. Here is a small voltage, not exactly 0 volt, but small. And then you have here some device. Okay, here maybe kettle or whatever it is heated. And now suppose you somehow it happens that you will be able to touch this piece here. Either this is connected to the body of the device, or like your isolation goes away and you touch it, or doesn't matter. If you touch it, and then you are here and grounded. Grounded meaning that here voltage is 0. And then current here goes through you, right? And goes to here. This means that if we have here a certain current I, then we have here I in and here is I out. Then I in minus I out equals the current which goes through you. And if this is larger than around 30 or 20 milliamps, then it is like dangerous for your life. And this device switches off as soon as this happens. It measures the current difference. And now the question is how to measure the current difference between two wires. How the device does it?
Using the same principle?
Sorry?
Using the same principle?
Yes, exactly, using the same principle. Suppose now here is one wire and here is another wire. If they are equal, there is no magnetic field here. So if they are different, then magnetic field appears. And you can just use that magnetic field to disconnect, right? But in general, you need to check if you have that fuse at your home or not, because that is very, you should have it because it makes much safer. Whatever happens, some broken electrical device while you are in bath, for instance, or taking shower, it's it can be very dangerous because there you are well grounded through those water through water to the ground. And if you are exposed now to the 130 volt, a very large current can go through you. All right, so that's about mutual inductance. So we spent more time than I planned originally, but seeing that you didn't remember what it was, I think it was still a little bit useful to recall what it was. All right. Now, we have reciprocity, and we have, I mentioned that similar thing happens in the case of mutual inductance, and then actually you have, we can have also mutual capacitance, because what is, if inductance is that we have voltage charge on one body induces certain voltage on it. So if you have many bodies, charge on one body can induce voltage on another body as well. So that is then that becomes then mutual capacitance. And of course, you have the same reciprocity ratio for the mutual capacitance as well. Now, going back to mutual reciprocity for electrical circuits. Actually, that's also quite useful thing to have, because you might remember things about Y delta equivalence. So raise your hand if you remember Y delta equivalence. Otto, usually remember we did problems. No. Norman.
The name is familiar.
Johan, do you remember Y delta equivalence?
I don't know the name. Maybe I'll know the concept when you get to it.
Okay, so that's basically, let me explain what it is. It tells you that if you have a certain connection of three resistors like that, R1, R2, R3, and another equivalent circuit like that. Okay, let me make like that. Now, the left one is delta, the right hand is Y, right? So that's why it's called Y delta. And the equivalence states that if you have arbitrary delta, and then there exists Y that has exactly the same properties in terms of those three terminals what you have here through three output leads. So you have always you can find Y that has exactly the same properties, and more specifically we can write even relationships between them. So we have R3 equals something like R1, R2 divided by R1 plus R2 plus R3. And if you want to express it reversely, then we would have R3 to the power of -1 equals R1 to -1 times R2 to -1 divided by R1 to -1 plus R2 to -1 plus R3 -1. So you have expressions that transfer one into the other. Now, actually, the theorem is more generic. So, the theorem actually says that if you have arbitrary system of resistors with 3 output leads, which have a connection in between them, with 3 output leads, then you can substitute either with properly chosen delta or properly chosen y. Now, how can we prove that this is true? What might be the problem? Okay, we have linear resistors, which means that we have linear response. What we need to characterize the arbitrary system of resistors is linear response. So let us say, well, if we let in a current to a certain pair of nodes. So suppose we have here node 1, node 2, node 3. Or maybe let us make it reduced by 1. So 0, 1, and 2. And let us keep it this always voltage regulated here voltage 0, right? And then we let in current to 1 and take 1 out from 0. So current I into 1 out of 0 is the first case. And then we have voltage appearing V1. I won't write 0 because it's always with respect to 0. V1 is going to be now certain proportionality factor R times index 1, meaning that I measure voltage between 0 and 1 when I let in current into 1, I1. And then we have also V2. Okay, we put here also indices. V21 is R21, I1, right? And then next case is when I let I into 2 and out of 0. All the other combination can be represented as a superposition of those two, because what is another possibility is that I take let into 1 and take out of 2. This is configuration A minus configuration B gives you this, right? Because in that case, what happens at 0, now 0 is that we take in and take in both with taking out, overall 0, nothing goes, right? So anything what we do can be with this circuit, it can be represented as the superposition of those two. And then we have V22 is R22 I2. V12 is R12 I2. And now we are 4 parameters that characterize it, right? But reciprocity tells us that those two are equal. And so we have left 3. So this circuit is parameterized by three parameters that have dimension of resistance, and here we have also three. So meaning that arbitrary response, we need to just have an equation for three unknowns here. We calculate responses over there. We calculate according to the responses, we find three equations for R1, R2, and R3, and find exact match for the arbitrary circuit. As you can see here, an important component in using of delta Y equivalence is actually the reciprocity. Without reciprocity, you wouldn't be sure it can be done, but now you are sure because you have degree of freedom for choosing delta or Y is 3, and here we have also only 3 parameters required to describe arbitrary circuit. Okay. Now, Y delta equivalence, that's a very useful thing because it makes normally by using delta Y equivalence, it makes it is the easiest way to calculate resistances in those cases when it won't break down into series and parallel connections, like bridge connections. If you try to solve it, find the effective efficient resistance between two nodes for bridge connections, normally it will be. By the way, did I start recording? Yeah, it started. Thanks. Okay. So, everything clear in this regard? But Otto, Norman, Mike, you don't remember us doing this?
I do remember.
Right. But right now we have a little bit more insight that why that works, basically. Why it works. Now, going on. Let us move on. And next thing is maybe you try to now move towards how to solve exactly, how to find exactly the lattice resistance, but before that still. This requires something like Fourier transform, and we will maybe to better understand why and what we are doing. Let us work before a little more with integral differential equations. Normally, during your university curriculum, you probably have solved a lot of differential equations in partial derivatives, in ordinary differential equations, but probably wouldn't have solved too many integral differential equations. Have you? Raise your hand if you solved any integral differential equations. Integral differential are sometimes also called non-local equations. What does it mean? It means that derivative in equation depends only on the immediate neighborhood. A derivative is just a difference between two very close points, right, nearby points. So a differential equation then how it evolves in the given point depends only on the immediate neighborhood. That's why it's called local. And meanwhile, non-local means that evolution, what happens here, depends also on things that are happening far away. And yeah, like we had here, so reciprocity theorem, it was also a global non-local theorem because it actually has a conclusion about the whole thing, not only its immediate neighbor. Now, can you suggest any equation or anything that could be non-local that would require not only things a little far away? Can you think of anything? All right, that is actually quite a simple everyday phenomenon that is non-local, and that is gravity waves on deep water. So waves behind boat are non-local actually. But let us talk about them a little later. Now, let us take another type of non-locality and consider fusion equation. But before we go to the fusion equation, before going to non-locality, let us just write the fusion equation. And then I use this another opportunity to tell you one more trick that is sometimes used when you deal with differential equations that are a little more complicated than normally. So the fusion equation will be, let us say, for temperature. But before, maybe let me drive it first. So you probably know expression for thermoflux P is conductance multiplied by gradient of temperature, right? Does it sound familiar? And then we have a continuity expression, which means that how much heat accumulates into a single point, it determines how much temperature will change. So we have C dt over dt. This is how much energy density, heat energy density in this given point is changing. And this is because of divergence of P. Here actually minus divergence of P. And this is divergence of kappa gradient T, and if kappa is constant, it becomes kappa Laplacian of T. Nabla squared, divergence Nabla, right? And this is called diffusion equation. So we have diffusivity D as kappa divided by C, so that dt over dt equals T Laplacian of T. And since we are going to, for our non-local equation, we're going to study this. We are going to study this in 2D. But before that, we would like to know how the solutions of this equation behave. And let us take in 1D. D over dt equals d and d squared t over dx squared. Do you still remember what was green function? Okay, then. We talked about green function. Mike, what was green function? Something. Norman, do you remember? No? Otto, do you remember what is green function? New guys, anyone? Green function? We had it there, right? Do you remember? Yeah. We had. Johan, what was green function?
It's a solution to the differential equation.
Repeat.
It's a solution to the differential equation.
And which solution?
The best.
Yeah, correct.
The best solution. It's a delta function solution, right?
Dirac delta function, yeah. When I have initial condition is a form of Dirac delta. Exactly, very good. So a green function is a solution of differential equation normally in partial derivatives for not necessarily, but usually for initial conditions a form of Dirac delta function. So we would like to find here solution for the condition that t at time equal to 0 equals Dirac delta function of x. And now, guys, tell me how can I find this green function? Any ways of finding the green function here? How would you solve this equation, diffusion equation, which initial condition is a form of Dirac delta? There are two good ways of doing it, maybe more, but to my mind comes two ways.
Fourier transform?
One is Fourier transform, yes. If I go to Fourier space, and then we can do, for instance, we go to take Fourier transform in space, then we have a dk over dt equals minus dk square dk, because derivative in Fourier space gradient goes to I times k. If we have derivative gradient in physical space, in Fourier space, it is just multiplying by wave vector times I. So which means that all the differential equations become algebraic equations in Fourier space. And that's why if you have, as long as, but it works only for linear equations. If you have nonlinearity, forget about it, because in that case, Fourier transform of a product is a convolution. And if you spoke about non-locality, convolution is non-local transform. And this makes you now non-local equation in Fourier space. But as long as you have linearity, it's nice. And then we have this equation, and then we can also take the transform the Fourier transform of initial condition. We obtain t of k equals 1 at t equal to 0. Initially, all components are ones. And solve it. But that's and that's a very nice way of doing it, but we are not going in this way right now. The other way is finding a self-similar solution, and that's exactly what I wanted to talk to you right now about. The other way is finding a self-similar solution. And what does it mean? It means while normally t is a function of x and t, but we are going to one variable instead. We try to guess what if we can substitute full 2 degrees of freedom into 1 degree of freedom. And for instance, something like we search a solution in the form of t equals, let us say, t to the power 5 bar and a certain function of x divided by t to the beta. And then we need to figure, then we have only, we denote this as psi. Then if this is psi, then we have, we had two variables, now we have one variable. So we'll be having coordinate differential equation now. But we need to find out what are alpha and beta. And now out of those, beta is defined by the structure of the equation. Alpha is defined by the boundary initial conditions. More specifically, let us see. If we make, if we plug in this expression here into a diffusion equation, we take this and plug into here. So what will happen? So basically, dt over what we'll be having is dt over dt is equal. First, we take a derivative by of this d alpha. This will be alpha d alpha minus 1, all right? And multiplied by f. And then we have the derivative for f, the alpha and f derivative, and general derivative of psi, that is, but then it becomes minus because we have minus beta now. Minus beta and x
Psi by t.
psi by t, yes, psi by t.
So it's also t to the alpha minus.
Let me, it's a little bit dirty here, let me try to make it. Minus beta. Now d square over d square. And then what? And then this will be no dependence on x here, so it will be d to alpha, and then d over d. Each time we take over x, we have that d to beta coming out, right? So we have a t to minus 2 beta, t to minus 2 beta is it f second derivative. Am I right? All right, and now we plug them into equation. We have alpha t alpha minus 1 f minus beta.
Beta psi t to alpha minus 1.
Sorry?
Beta psi t to alpha minus 1.
The alpha minus 1, yes. Alpha minus 1 f prime.
Psi.
And psi. And equals d t alpha minus 2 beta f second derivative. And now what we would like to have is to get rid of t's. No problem with just 2 are equal. All we need to have is that they all equal to that here. So we need to have alpha minus 1 equals alpha minus 2 beta. Right. Which means that beta is 1/2. As I said, beta is determined by the structure of the equation. Because alpha doesn't matter here in this relationship. So beta must be 1/2. Now, how do we determine what is alpha? And alpha is determined by, as I said, by initial and boundary conditions. And in this case, we have actually one conservation law for this equation. What is the conservation law we have here? Integral of motion. Overall heat. Because if we take this equation and integrate this over x, we multiply this by dx and integrate. Then we have a d of t of integral t dx equals, and now if we take this is d and dt over dx, difference between minus infinity and plus infinity, and normally you expect them to be zeros in both at both ends, so it is zero. So it means that this is conserved here, right? Now, if we have a solution like that, we would need to have this conservation law, right? So it becomes t, the factor here depends how the height changes. And beta over here depends how width changes. So basically what we need to have is the brake factor t alpha height multiplied by the width, which is t to beta. And they must give us a t to 0, no dependence, which means that alpha equals minus beta. Which means that alpha is minus 1.
What was this? Why did you do it to the alpha test?
This is height. Height of d alpha f of x divided by d beta. Right? And that is the width. So we have a certain profile for our temperature. This here is T to alpha. This here is T to beta. So a surface area total is height times width. Right? Shape factor as well, but shape factor is defined by f. This shape factor remains constant. You can do it properly if you'd like by taking integrals and plugging in, but the result will be the same. If it's too sloppy for you, but I think it's okay.
I like it a lot.
Ah.
I like it a lot.
Okay, good. And then here now we have now finally we can write down our equation. We have beta 1/2, alpha is minus 1/2. Then our equation is like this. Somewhere here we have this right over here. Let us plug in. Alpha is minus 1/2. Minus 1/2 f. Beta is 1/2. Still minus 1/2, and but these drop out, right? Because of this condition. I don't need to worry about these. Then it will be f prime times psi. And all that equals to d and f second derivative. Or we can rewrite it as d f second derivative 2 times plus f derivative psi plus f equal to 0. Okay, now we have ordinary differential equation. How to solve this? Well, this is another question, but it's linear differential equation which varying constantly. You probably can do it. It has also conservation laws in this equation because, or maybe not. Anyway, maybe not. But anyway, you can solve it. And this is actually your Gaussian function. You can just try looking here for some solution. You know that if you have linear differential equation, if you can guess solution, you're done. Because any solution will be a linear combination of the of the solutions linear combination of the solutions, any particular solution you can find. So if this is second order differentiation, in principle you would need to have two independent solutions, and then you have found everything. But I think here only one works for us, because we have additional constraint that we would like to expect f go to 0 at left and at right hand side. So because of that, if you manage to find one single solution that satisfies those boundary conditions, that going to 0 at plus minus infinity, then you are done. So we would like to have f goes to 0 if x goes to plus minus infinity. And then you can look, for instance, solutions in form of E minus something like a gamma times x square, and plug in, phi square. Plug in and see if you can find if this works. But it does work. And then I think it should be something like, actually what will be is e to the power minus psi squared divided by 4d will be probably the solution here. All right.
I remember seeing a different solution, way to solve this equation with half derivatives.
Okay.
So you'd do a squared minus b squared is a minus b, a plus b, with the starting equation, and you'd have half derivatives there.
Square root of derivatives, I mean.
Yeah.
Yeah, that's a little bit different thing. We are not. This is not a solution of that, because square root of derivative, we are going to square root of derivative, but that is exactly a non-local operation. So this gives you integral differential equation.
Mm-hmm.
And so but that's not all here. So what we obtained here is a green function. But there is also another self-similar solution here that is possible if we take another initial condition. So if our initial condition is t at x equal to 0 is t0 is fixed. Then what?
So we have it in contact with something, or what?
Yeah, like you have a board here, you attach something heating and keeping this end here at constant temperature, right? And how temperature will propagate, for instance. And then we are again can look for self-similar solution, and then we'll be having something like still we have look in the same form, and still we have beta equals 1/2, right? Because this beta equals 1/2 doesn't depend on the boundary and initial conditions. This is defined by the structure of equation. So we still have beta equals 1/2. But what is alpha now?
Zero.
Yes. Because as said, beta defines the width how behaves. Alpha defines how height will change. And right now we want height not to change. So alpha is 0. And so now we would like to find what is the profile now. Let me now rewrite this equation as well. Here, what equation do we have now? And because now alpha is 0, then this term here goes away. And we have still exactly the same equation that is here, but without this guy over here. So now we have 2d f segment derivative plus f derivative times psi equal to 0. How to solve this? This is a little easier to solve than the previous one, right? Isn't it?
Yeah.
The previous, I just to save time, I just gave you the solution, but here we can do it. So, Todor, can you solve it?
Yeah, I'd say f double derivative is df prime by dxi, and I'd separate the two. It's a bit non-rigorous, but that's what I'd do.
Okay, so our new variable is f prime. Let's
Yeah,
G. This is G.
So now,
So we have 2d dt divided by dxi plus xi equal to 0. This is a nice equation with separable variables.
plus gxi, plus g times xi.
Yeah, xi times g. Yeah, and so with separable variables, so we have 2d dt divided by g equals minus xi dxi, and because of that, we have 4d logarithm of g equals minus xi square, and g equals e to the power minus xi square divided by 4d. And now let us recall that we need to integrate, and f equals integral of e minus xi square divided by 4d equals dxi equals f function of now f is psi divided by how is f?
I don't remember.
From where to where? Let me just check. F is from infinity.
No.
F is from 0 to x e minus t squared dt. And that is also 2 divided by square, but we don't care about prefactor right now. F is from 0 to x, so it will be, yeah, so we can just safely write it as xi divided by 2 square root of g. And there you have it. So here the solution is an f function.
1 minus f or something? Or
Sorry?
is it 1 minus f?
Right. We want to have, so the f is from 0 to x. You are right. It is 1 minus f because we want our solution to go to 0 at infinity. So f plus constant, because integrate plus constant. And we now we need to find our constant. And here is actually also another constant. Let me, instead of constant, let me write a and b. A plus b. And now we can, we need to have this to go to infinity, 0 if xi goes to infinity, f goes to unity if it goes to infinity. So we must have so opposite to each other. So we take F equals 1 minus F of psi divided by 2 square root of d. And now let us write it also in terms of initial variables. And this will be 1 minus F of, and psi was x divided by
It's divided by half of square root of t.
Psi was x divided by square root of t. So it is x divided by 2 square root of dt.
And
Okay, and I think that's it.
we can get total temperature from this.
Sorry?
And we can get total temperature from this and see how much energy flowed in.
Yeah, sure. I can get everything from here now. So now, what is the lesson here? That if there are equations that you might not be able to solve as is, but if you can figure out some useful self-similar solution that might make sense in your case, then you might be able to find that particular solution. Not every solution, but the solution what you are interested in. And now, so self-similar solutions, they are good and they are bad. Good ones are the stable ones. Like if you take those diffusion equations, self-similar solutions, they are good because if you take initially not Dirac delta function, but something different, it asymptotically will start approaching the self-similar solution. So your self-similar solution is, in that case, very representative in almost all cases. Yeah, at the end of the day, you will have that self-similar solution. This is not any arbitrary solution, but very important solution in that case. And the same happens with the boundary condition. If your boundary condition isn't that you switch it immediately on, but maybe some time during some time interval delta t, and then if you wait, asymptotically we're still approaching this F solution later on. All right, so now we obtained, actually wanted to have this second solution, because that second solution will be a basis for us to find what Tudor was mentioning here before, like going to fractional derivative. So what will be we'll be doing next time is we'll use this solution that we obtained. And consider another situation when you have like maybe a hot plate here, and which has very good, not hot plate, plate which has good heat conductivity. And then you have beneath, you have something which has not that good conductivity, like metal on top and some non-metallic material below. And then you start put here at the one end of the plate, you start heating. Heat will very fast propagate along the plate, but it will losing across the plate. And this result here helps us to connect those two and obtain one equation for temperature penetration along the plate, but that will be now non-local. That will be doing next time. And then we have a look at what can we do, how can we solve it, and from there we move to the this will be a continuous version of non-local equations, and then we move to the discrete version that is the infinite grid of resistors. That is the plan. Hopefully you will manage to complete both next time. Right, any questions? Oh, homework. Let O be finding a self-similar solution for a nonlinear diffusion equation. A nonlinear diffusion equation is that you have d over t equals d over dx. And now let us say the diffusion coefficient is depends on temperature, and let us say, simplify it, let us say this just proportional to temperature. T over d. This is nonlinear diffusion equation. And we could have here also prefactor, but we can lose prefactor by renormalizing the, let us say, time and t and x, so we can get rid of the prefactor. So I'm not writing it here. So you can, if we had here d, we could say that okay, we have t prime equals t divided by d, and then in t prime d would go away. So now, sorry, that's why we won't need to have here constant prefactor. So another diffusion equation, and try finding the same self-similar solution. Dirac delta function, t equal to 0 equal Dirac delta function of x. T x equal to 0 equals Heaviside function. Basically, what we did was we have a Heaviside function, we switch it on, right? Heaviside function of t. Raise your hand if you know what is Heaviside. You can sometimes call it also theta function. This is 1 if t is larger than 0, and 0 if t is smaller than 0. That's what we solved. Second self-similar that we found in black here. It was with the Heaviside function. There are more types to self-similar solutions. For instance, there are shock waves and solitons, but we'll be discussing them again also, but a little later. So we go at the end of the course, we'll be having solitons, and we'll be discussing those shockwave type solitons and shockwave type solutions and soliton like solutions towards the end of our course. Skipping them here. So, any questions?
This is quite different from what we did, but when we did the Y delta equivalence, why was the reverse transformation everything to the power of -1?
Once again?
So we did the delta Y transformation.
Yeah.
When we went from Y to delta, it was the same thing, but everything was 1 over.
Yeah.
Is there a nice reason for that, or?
There might be, but that is probably, I would say this is Wallish current equivalence. That is a different topic.
Okay.
When Wallish becomes current and current becomes Wallish. It can happen in 2D. In 3D, it cannot happen, but you can, like, kind of flat. The question is, you have 2D graphs or 3D graphs, but you can kind of flatten 3D graphs also, like it's a project into the plane.
Yeah, I just didn't see how to do it.
Okay. Yeah. All right. Any more questions? Anyone wanted to give homework? I have you here. All right. Until next time. And working with the meeting with Tartu University PhD students.